Nice to see all of you for this meet. I do not know how many of you can still follow me, but then I do not want this one-way conversation for now. Um, so, guys, before I start, I wanted to know if you all are uh, like if you do have a paper on nanotechnology as a subject. Do you guys have nanotechnology as a subject in your curriculum?
Someone of them is like some topics inside another subject.
Okay, so if some topics are inside, then they must definitely know about what nanotechnology is.
Vocês sabem, né, gente, sobre tecnologia, nanotecnologia?
Yes, Gomathi.
Tá todo mundo tímido,
Yeah,
acordem.
thank you, thank you. Yeah, I could see your Professor Mairim answering me, but then I'm not here to talk to Professor Mairim. I'm here to talk to her students. Can I hear some other voices other than Professor Mairim's?
Yes.
Yes, I know. I know Anna Maria will be the first person to come up and say that yes. Well, fine, guys. Now I take positively that you people are studying nanotechnology, which means that you know the basics of nanotechnology. You know the basics of a nanoparticle. You know about the properties of a nanoparticle. So I take it you're aware of things like gold particles, silver nanoparticles, carbon nanotubes, graphene oxide nanoparticle, titanium oxide nanoparticle, zinc oxide, cerium oxide nanoparticles. And I hope that you guys are aware that these nanoparticles do exist and they contribute a lot to the welfare of humanity. Are you guys with me? Are you guys following me? Yeah, I understand, Madam. Entendi. Your internet is a problem.
No, I'm not sure if it's my signal or is yours.
Okay, it is. I think then it must be my signal. Do you have problem in listening to me?
No, now I am listening. Okay.
But before, did you?
Yes.
So the problem is with me.
Oh, okay. So I think
No,
then that
no.
must be from.
I think the problem is with her because it stopped
Yeah,
the.
because it is raining heavily, and it is 18 hours night. So everybody must be using internet at homes. That is the problem, I suppose. So it's dark and it's raining here. So if you guys could not follow me, please do let me know. Sayani has got something to tell. Esther, Escutando, Thambem. What was that? It is?
She is listening too.
Oh, she's listening. Thank you, Pravose Tambe. Pravose Tambe. Right or wrong? I'm sorry. Okay, guys. So long I was talking about that you guys are aware of nanoparticles. You guys are aware of the physical characteristics and the chemical characteristics of a nanoparticle, and I hope you must be aware that there are a lot of nanoparticles that have seeked a much importance. Say for example, the gold nanoparticle, silver nanoparticle, titanium oxide, cerium oxide nanoparticles, carbon nanotubes, graphene oxide nanoparticles, magnetic nanoparticles for that matter. So, anyway, I'm not going to dig deep into the kind of nanoparticles and their activity. I am going to explain things in very short, for a very short time, and it is going to be 3 research work what I had experienced. So before I start sharing my slides, I do have something, again, a story to tell you, like how did this work happen? So let me start sharing the slides. 1 minute. Yeah. Yes. Anna Maria, help me if my screen is visible.
Okay.
Yeah, can you tell me if my screen is visible?
Yes, it is.
Thank you. Thank you. So, guys, this is my topic. Look for tomorrow, nanotechnology in action. If you ask me why this topic, because why tomorrow, not today? Say for one single reason. See, today's nanotechnology is everywhere only in the laboratory. So it is like all along the bench side, it is in the lab and it has not reached the land. That is what we call lab to land, which means you are implementing it for the commercial purpose or for the domestic purpose of human beings. But unfortunately, today's nanotechnology plays a dominant role in laboratory. That is the reason why I had framed this topic as look for tomorrow, because nanotechnology will be in action only tomorrow, whereas today it is all under research. So with that small note, you could see a picture like this is one of the paper that we published very long back, probably in the year 2014 if I'm not wrong, in the paper Langmuir in American Chemical Society, entitled In Vitro Bacterial Cytotoxicity of CNTs, Reactive Oxygen Species Mediate Cell Damages over Direct Physical Puncturing. So if you ask me what happened and why this publication, again, everything starts with a very small story. Friends, you know, once what happened in our laboratory, one of my friend was working with carbon nanotubes, and we were assessing its bactericidal property. I mean, the property of its bacterial killing action. We were actually quantifying what could be the percentage of these nanotubes that can kill bacteria. Now, the second point is we did not prepare the carbon nanotubes, but then we procured, which means we bought it from the Waltham and Bentham laboratory. So it was something that we procured from America, and we had those carbon nanotubes with us. And since it was a microbiology laboratory, this paper got published in the year 2014. But it took us 2 long years, 2 full years for us to come out with this paper. So the work started long back in the year 2010, 2010. So what happened was, friends, yeah, tell me, Anna Maria.
Gomathi, you stopped to share your screen. I don't know,
No,
it
no, no, no.
was on
No,
purpose.
wait, yeah, I'll do it again. 1 minute, Anna
Thank you.
Maria.
Thank you.
Okay, a window, and oh, yeah. Okay, I think now it is visible. So this all started with this carbon nanotubes that we procured from Waltham and Bentham laboratory. So what we were actually doing was, in the year 2010, what we were actually assessing was, we had a few nanoparticles prepared by ourselves in the lab, and we also bought some carbon nanotubes from Waltham and Bentham laboratory, and we actually wanted to compare the quality of the carbon nanotubes that we bought with the quality of the carbon nanotubes that we had manufactured or we had synthesized in our laboratory, in the laboratory called Advanced Material Devices. So at that time, we were working on antibacterial activity. I hope all of you must be knowing what antibacterial activity is. You streak a bacteria on the Petri plate, you make a well, you load the nanoparticles, and you look for the zone of inhibition. So it was a very simple work that we were actually planning, and we were also working on it, not just plan, we were also working on it. So one day what happened, my collaborator and myself, when we were working,
Gomathi.
He was supposed to add the carbon nanotubes to the bacteria in the night, inoculate them, and then in the morning, I will be taking back the work and continuing with the rest of the work. So unfortunately, what happened that night, my collaborator, he was so sleepy. He was, I think it must be around midnight, 2 o'clock or 3 o'clock. He did the work, but he forgot to do one thing. He forgot to put back the conical flask back to the rotary shaker. I repeat, there was a conical flask with the media, which was inoculated with a few pathogens like Escherichia coli, Shigella soni, Bacillus subtilis, Pseudomonas aeruginosa. So we inoculated those bacterial species to the media, and then we also put some carbon nanotubes inside the conical flask. But the only thing what he forgot to do was he forgot to remove the conical flask from the chamber, and he forgot to drop it in the rotary flask. So morning 6 o'clock when I returned to the lab, I saw that there was, yeah.
Sorry, are you sharing the PowerPoint or the paper, the manuscript?
I'm not sharing the manuscript, friend. I'm just showing the title because the story I have not typed on the slide. So I thought people could see it.
Okay.
I'm actually telling the story of how this work started.
Okay, so you are sharing the title. Okay.
Yeah, I'm sharing the slide. May I know if my slide is visible?
Yes.
Okay, thank you. Okay.
This
so
is a print screen.
Yeah, guys,
okay.
Yeah, guys, I'm telling the story. I'm actually telling you the story of how this work has happened. So long, he forgot to put the conical flask in the rotary flask shaker. So the next morning when I came back to laboratory, I found that there was no conical flask in the rotary shaker. And when I went and checked inside the inoculation room, guys, a minute, Amma, pathram tekadinga, Amma. So when I went and checked in the laboratory, there was no conical flask in the shaker. And what happened was, when I went and checked the conical flask, I could see a lot of bacteria that was grown inside the conical flask. Initially, we could not understand what happened because my friend was telling me that he mixed both the bacteria and the carbon nanotubes. So, technically, if I mix bacteria with carbon nanotubes in the media, the carbon nanotubes are supposed to kill the bacteria. And in the year 2010, it was proved all over the world that carbon nanotubes actually pricked the bacteria, or it edged the bacteria, which means it rubbed the surface of the bacteria, and as a result, the bacteria died. So technically, even if we don't put the bacteria, even if I don't put the conical flask in the rotary flask shaker, the bacteria are supposed to die. But the bacteria did not die. So what we did was, we first checked if the carbon nanotubes are added to the conical flask. And then we confirmed that, yes, carbon nanotubes were added. Then there was a question, how could the carbon nanotubes stay just like that without killing the bacteria? So this was our question, and this is how we came up with this research work. So what happened exactly was, friends, we took 4 different bacteria, as I told you, Escherichia coli, Shigella soni, Klebsiella pneumoniae, and Pseudomonas aeruginosa, and we mixed them with carbon nanotubes, and we found out that these carbon nanotubes, they behave differently in light and they behave differently in dark. So in light, we could see that there was antibacterial activity, whereas in the dark, because all these conical flasks which were kept in the incubation chamber used to also be a dark chamber, so therefore we could not find any antibacterial activity when all these things were kept in the dark. So now here came a question. Do carbon nanotubes behave differently between light and dark? And then in order to answer this question, we proceeded with the next topic, like we saw if the carbon nanotubes could puncture or could rub the surface, but then we also found out that these carbon nanotubes were found to be effective generators of radical oxygen species. So now the second part of our work, what we did was we tested if these nanoparticles could generate reactive oxygen species. However, we just took three radicals. One was singlet oxygen radical, and the second one was superoxide radical, and the third one was hydroxy radical. I repeat, we tested only for just three oxy radical species. One was singlet oxygen, the second one was superoxide, and the third one was hydroxyl radical. So, using experimental condition, we tested if the carbon nanotubes could generate these three oxy radicals. And we also found out that these oxy radicals were generated in the presence of light. Whereas in the dark, in the presence of water, carbon nanotubes did not generate all these three oxy radicals. So now one thing was sure from us, that ambient is room condition. So we could see that in the presence of water and in the presence of sunlight and in the presence of normal light, carbon nanotubes were capable of oxy radical production. Whereas in dark, carbon nanotubes did not produce reactive oxygen species. In order to further confirm, all of us know that oxy radicals can be counteracted with antioxidants. I hope this you all must be knowing. So now the third part of our work was, now if this could generate oxy radicals, now let us see if we could coat it with antioxidants, if this carbon nanotubes could mask the oxy radical generation. So what we did was, we took some naked carbon nanotubes, one group, and the other group was tannic acid functionalized nanotubes. Friends, if you could ask me why tannic acid, in reality, we actually choose tannic acid and gallic acid, the phenolic acids. And we also chose quercetin, epigenin, and catagen to functionalize with carbon nanotubes. But unfortunately, when we took flavonoids such as catagen, epigenin, and epigenin, catagen, rutin, or quercetin, what we found was the functionalization was not very effective, and these compounds started to lose its property when the temperature was increased from the ambient condition. Whereas the phenolic acids such as tannic acid and gallic acid, they behaved differently because there was no loss, and we could obtain a very good functionalization. So now the second thing what we did was, we saw if the naked carbon nanotubes could produce oxyradical species, can also the tannic acid functionalized carbon nanotubes produce? Then we found out that the tannic acid functionalized carbon nanotubes did not produce oxyradical species. Therefore, we thereby confirmed that the process or the true mechanism behind bacterial cytotoxicity, behind killing, was not puncturing. Carbon nanotubes did not puncture. Carbon nanotubes did not edge, which means it did not rub the surface, whereas carbon nanotubes, even though they are not in contact with the bacteria, even though they are far from the bacteria, all the reactive oxygen species that are produced in the presence of light actually killed the pathogenic bacteria. So therefore, we finalized that the reactive oxygen species produced by carbon nanotubes was directly proportional to the bacterial cell mortality, which came out as a very good publication in the paper Langmuir. And as of now, we have got somewhere around 48 citations and 1,100 article view. you could see a small picture here that the carbon nanotubes produce oxyradical species. So these ROS generation, even though they are far from bacteria, were capable of damaging bacterial cell wall. And all of you know that the minute the bacterial cell wall is being damaged, there will be leaching of its cytoplasm and nucleic acid. So when there is a leaching of both nucleic acid and cytoplasm, obviously the bacteria died. So this is the first part of my work, which I was trying to show you. Friends, do you have anything to ask me? Guys, can I proceed with the next work?
Yes.
Thank you.
Yes.
Thank you. Thank you. And
Bom,
so,
Gomathi,
yeah,
the formulation de desses carbon,
carbon nanotubes.
carbon
Yes.
carbon nanodrugs, de recipientes farmacêuticos, the formulation.
The formulation, yeah, see, it was all carbon material, but what I'm trying to tell you is we did not synthesize. What we synthesized were from the pure carbon atoms. The carbon nanotubes that we produced were from pure carbon material, but then we also had procured it from Waltham and Bentham laboratory, and they both behaved differently. It was not the same that what we could produce, because if you try to produce carbon nanotubes by plasma arcing, we always found that there were some surface characteristic property which gave us different carbon nanotubes with different properties.
Okay, thank you.
You got my point? Like did you understand what I was trying to tell you? Anna Maria, can you help me if Saulo could, did he receive the point? But because plasma arcing, the plasma arcing method of carbon nanotube production, even if there is a mild difference in the temperature, even if there are some impurities in the carbon material that we used, the nanoparticle characteristics vary differently between every time that we synthesized.
Saulo, você entendeu? Tá com o áudio fechado.
Eu entendi muito pouco, Ana Maria, agora.
Ela quis dizer que qualquer mudança da composição muda a característica físico-química, né?
Ah, sim, sim.
Da formulação. E aí você tem uma formulação completamente diferente.
I think now he understood.
Agora,
Yes.
eu tinha entendido só um pouco disso, não entendi tudo, não.
Thank you.
Obrigado, Ana Maria. Obrigado.
Yeah.
Thank you, Gomathi.
You know what happened? The carbon nanotubes that we produced were not that toxic. It actually did not show antibacterial activity. They were actually biocompatible. Yes.
Entendeu?
That is why I told you the particles showed high variation. Okay. So, yeah, Anna Maria, I'm just continuing.
He understood.
Yeah, thank you.
You're welcome. You stop it to share again.
Yes, I'm again sharing it.
Okay, thank you.
You know what is the best part being a teacher? When you have doubts, when the students come up with a lot of doubts, that is the happiest part. So that's the reason I put off my slide sharing. Okay. So the second work. At the same time, when we were working with carbon nanotubes, we also were working with silver nanoparticles. And this preparation of silver nanoparticle is not very difficult, because all of you must be knowing that using sodium hydrotetraborate, you use as a surfactant, and then you try to reduce the silver nanoparticle, which is a very commonly used method to prepare silver nanoparticle. But then what I'm showing you here is something that we did some 12 years back. This is not new. So some 12 years back, synthesizing silver nanoparticle using co-precipitation was just budding out. It was just the start in the field of nanotechnology. So what I'm showing you is the work that we have done some 12 years back, and then after some 2 or 3 years, we got it published. So this is a very simple silver nanoparticles that we actually synthesized using co-precipitation method. Now, what we actually did was we controlled its size and shape by using its hydrophobicity, which means we had a different concentration of sodium tetrahydroborate with different molar concentration of silver nitrate, which showed we had different size and shape controlled silver nanoparticles. Therefore, by varying the concentration of sodium hydrotetraborate, so this one, and by varying the concentration of silver nitrate, we were able to obtain some different size and shape controlled silver nanoparticles. The next step
Travou só pra mim, gente. Pra vocês também.
Travou aqui. Tá travado.
Travado também.
Guys, can you hear me?
Now we can.
Yeah, I'm sorry, I had a call and I was supposed to take it. Thank you. I'm sorry, guys. So we obtained silver kind of different nanoparticles. So now what we did was, now we tried to apply them on the fabric surface because we were working for some wound healing activity where they used to tie cotton cloth around wounds in order to prevent from further infection. So this was our basic idea. And slowly what we did was, we confirmed that all the nanoparticles be synthesized using co-precipitation method, were different in size, were different in shape, based on the scanning electron microscopy, X-ray diffraction studies, and energy dispersive spectroscopes. So number one, we were confirmed. It is confirmed that all these are different. Now number two, when we tried to check for its antibacterial activity, we cut small fragments of the fabric. I mean, the fabric were cut into small pieces, and then it was all kept on the plate and it was checked for the zone of inhibition. So what actually happened was, so this is the image that you can see that. See, now this is the in situ silver nanoparticle on cotton fabric that we have done by tuning the silver source concentration. So you could see this is 0.01 millimolar AgNO3, 0.5 millimolar, 1 millimolar, and 10 millimolar, where you could very well clearly see that there is the difference in its shape and size. So you could see that there is a difference in the shape and in the size. You could see these were all very round, but whereas when the concentration of AgNO3 increased, the particle size were more clear. So this is one. And then here again we tested with the reducing agent, which means with a varying concentration of sodium tetrahydroborate. And again here you could see that there are differences in the size and the shape of the nanoparticles. So this was our first thing. So this we were confirmed. And here, I'm sorry, and here this is the X-ray diffraction studies that we use. So this are the antibacterial activity. So this cloth was produced by this method, cotton fabric. You substitute it with silver nanoparticle. You add some more layer, you add some more layer, and you add some more layer. But whereas the cotton fabric and the silver nanoparticles were like this, where you could see when substituted, somewhere around 1 millimolar concentration or the silver oxide nanoparticle in higher concentration showed a big zone of inhibition using bacteria Shigella soni. Guys, excuse me. Guys, we actually took so many different bacterial concentrations, but then what I have showed you here as a picture is using Shigella soni. Of course, they behaved differently for different group of bacteria. So depending upon this, the cotton fabric showed a very good zone of inhibition, which showed us that when we supplement this to the cotton fabric in the future, I think so long people are just using silver meshes, but not silver oxide nanoparticle substituted cotton fabrics. These nanofabrics are not in usage. So slowly, when these nanoparticles, when all these are coated onto the fabric, this could make the surgery more easier. In case of all internal and external sutures, if these cotton material are being coated with silver oxide nanoparticles that has been reduced, I think this could pave way for a very good surgical equipment. So this was the silver loading capacity. And guys, and something that I could also tell you is it was durable even up to 30 washes. When we washed these cotton fabrics, we could see the presence of silver oxide nanoparticle and the durability of these silver nanoparticles on the cotton fabric. They lasted for 30 washes. So the durability is around 30 washes. But then if you wanted to have it a prolonged durability, then it is in the hands of you guys that you must come up with some good method where you can find it highly durable. So uh, this is one work that I would like to share with you. And guys, do you wanted to ask me something? Yeah, Carla has raised something. Can I ask you, Carla, what is it? Carla Maria, do you want me to ask something? Guys, this is the second story and this is the second publication of the day. I'm not going to proceed anything further. So if you guys have got something to ask me, you can please ask me and then I can proceed.
The size of the nanocapsules influenced in the results, antibacterial results. Which
1 millimolar concentration, 1 millimolar concentration, and 10 millimolar concentration also had a very good activity.
Okay, thank you. And you didn't put any active principle, any substance, like drugs?
No. Silver oxide nanoparticle itself is what can I say? Has got antibacterial activity. So
Yeah.
we did not supplement this with any other material.
Okay, thank you.
Gomathi,
Yeah.
can I talk to them just a little bit in Portuguese?
Yes, of course you can, friend, please.
Because this is a different subject, maybe someone don't have this, so I'll try to explain.
Yeah,
Vocês
thank
estão
you.
me vendo? Gente, é o seguinte, é porque é uma coisa bem específica, tá? Tipo, não é todo mundo que trabalha com antibacteriano, antioxidante e com nanopartículas. Então, às vezes a gente tá escutando, a gente entende no inglês, mas a gente também não consegue entender porque é diferente, uma área diferente. Ai, meu Deus, espera aí que minha bateria tá acabando. Só um pouquinho. Tá me ouvindo?
Sim.
Tá,
Sim.
Sim.
Só um pouquinho.
Okay, they are telling you yes. I do not know what is this yes for.
No, it's for me, don't worry. It's for me. Just a minute. Tá. Primeiro ela falou dos nanotubos de carbono, né? Que ela foi contando uma história que foi muito didática, que até me lembrou a história da descoberta da penicilina, né? Deixaram lá no laboratório e foram vendo o crescimento da bactéria ou não. E aí depois foi verificar que teve... Porque quando tem espécies reativas de oxigênio, essas espécies podem ser danosas para bactérias ou elas podem ser, assim como as substâncias são antioxidantes, elas podem ser antibacterianas também. Então, tudo depende da via. Lembra que ela testou 3 diferentes espécies reativas ao oxigênio, né? Que foi hidroxila, eu não lembro as outras. oxigênio ali, eu não me lembro qual foram. Então, ela testou 3 diferentes espécies. Aí ela foi para o segundo experimento. Antes, ela só testou esse nanotubo de carbono, tá? Carbonos nanotubes, tipo, não tem drogas lá, era só uma formulação com nanotubo, e aí ela estava tentando, eles não trabalham com um princípio ativo, com drogas, né, mais essa tecnologia. E daí agora, nesse segundo momento, eles podem incorporar prata, tá? Tem outro nome. Ai, como alguém sabe em português isso, não sei o que, não é sulfato de prata. Friend, é o ginato of prata is just silver?
Silver oxide nanoparticle, friend.
So just silver inside the nanoparticle.
Silver nitrate, yes, reduced silver nitrate, and we reduced it using
Nitrato.
sodium
Nitrato de
tetrahydroborate.
prata.
Tá, nitrato de prata. Então já é uma substância que há muitos anos se usa como antibacteriano. Tá? A gente até tem uma patente que a gente fez alguma nanopartícula também, então já se usa, por isso que ela falou que não é nada novo, é uma técnica mais antiga. Então se usa essa nanopartículas com prata, porque ela já tem essa função antibacteriana. E aí, pelo que eu entendi, eles se incorporaram em tecidos de algodão. Sulfadiazina, isso, a sulfadiazina de prata, que é muito utilizada, é uma pomada para queimadura. Essa segunda história que ela está contando é justamente para testar, ela falou, né, queimadura de pele, acho que ela falou isso. É para testar em queimadura, então, por isso que tá tudo correlacionado e não é todo mundo que vai entender tudo, porque como ela está fazendo antibacteriano, quando a gente tem uma ferida, tem a produção de bactérias, e a sulfadiazina de prata se utiliza como esse processo de queimadura, mas eu acho que porque ela tem atividade antibacteriana, então já vai prevenir o crescimento de bactérias, não tanto pela atividade de cicatrização, né? Acho que é isso, Alex, não é muito a minha área, mas acho que é isso. Então é isso que ela está explicando, fizeram uma formulação com a prata e colocaram nesses placa de Petri, né, para ver a atividade antibacteriana. Então, daí tá vendo que tem atividade para algumas bactérias, e aí incorporaram, quando ela falou o mesh, lembram que o mesh serve para vários termos, né, que nem scaffold, para várias coisas, scaffold, mesh, serve para várias coisas. Então, pelo que eu entendi, eles colocaram num tecido, né, de algodão, e ela falou que na lavagem até dava para detectar, né. Então, para quem acompanhou lá no Left, a Paula Menezes, ela fez um trabalho assim, que ela impregnava nanopartículas em meias, né, para compressão. Então, as partículas estavam ali dentro daquelas meias. Impregnava no tecido. Então, é isso que eles estão querendo fazer, tá? Tem várias ideias, tipo, fazer meias, por exemplo. Tive uma aluna, né, não sei quem acompanhou, Graça. O projeto dela era fazer micropartículas para impregnar em meias para a sudorese, que tem um termo específico para sudorese, que eu não me lembro. Para o chulé, tá, gente? Não lembro o termo disso aí, como é esse termo em português. E aí, então, é nesse sentido que ela está falando, tá? Incorporar em tecidos para ver se a função antibacteriana. Entenderam? Só para esclarecer alguns pontos, que como não é muito da área, né? Então, beleza. Gomathi,
Yes.
you can proceed.
Yeah, friend, this carbon nanotube work was a very, very, very hectic work, and I also wanted you to translate even that to your students, friend, because before what we found, for 10 long years, right from the year 2000, people believed that carbon nanotubes kill bacteria by puncturing, or they rub on its surface, and that is why the killing was caused. But after 10 years, after a decade, we found that carbon nanotubes need not touch bacteria. Only in the presence of light, carbon nanotubes were capable of producing oxyradical species. And these oxyradical species could transport in the water medium, not in the dry medium. So these oxyradical species, the minute they touch on the bacterial cell wall, it caused a damage, and with that small damage, the cytoplasm of the bacteria oozed out, the nucleic acid of the bacteria oozed out, and therefore the bacteria died. So therefore, after 10 long years, we showed through this paper that the bactericidal activity of carbon nanotube was not physical puncturing, was not physical contact, but it was reactive oxygen species in the presence of light, not in the dark.
Sim, é isso que ela estava falando, que antigamente, há mais de 10 anos, se acreditava que esses nanotubos de carbono tinham essa função antibacteriana. Só que aí, com o experimento deles, por isso que é muito importante, e foi muito legal ela contar como uma história, né? Aí descobriram que não era um contato físico, que simplesmente o nanotubo, essas partículas, né, iriam matar a bactéria. Então, ela tinha um mecanismo que ela gerava espécies reativas e, em meio aquoso, transportava essas espécies reativas para a bactéria, e essas espécies reativas, sim, tinham alguma função, né, contra a bactéria. Só que ela... acho que é isso. Tem mais alguma coisa para acrescentar, Ana Maria? Acho que eu me perdi no raciocínio.
Que era na luz também, né? Não era
Sim, na presença da luz,
Isso.
só na presença da luz, porque a luz, né, que faz essa geração, auxilia na geração dos radicais livres. Lembre-se que na luz solar, quando a gente vai no sol, às vezes a gente se queima, né, tem manchas por causa da geração de radicais livres, que é um dos mecanismos que gera radicais livres, é a presença da luz. Então, foi isso que foi descoberto. Friend, congratulations about your paper.
Oh, come on. I was not the first author, friend. It was my collaborator, Rajvel, who was the first author.
No worries, but you are...
Author.
Yeah, okay.
Yeah, but then, friend, unfortunately, it took 2 years of our lives. 2 full years of both of our lives. It literally killed our life, because for both of them, this was not our PhD work. But we did not know what is actually happening. So 2 full years, friend. Done.
Yeah, this is a beautiful story. It's like science. This is science.
Yes. Okay. So now this is the last part of the story. Now this is the continuation of the first story. So when we showed that tannic acid functionalized carbon nanotubes did not produce oxyradical species, there was a question from one reviewer that how can these tannic acid get functionalized into carbon nanotubes? So now the slides that I'm going to show you is the third part of the story. I mean, which is the very, very simple story and a very short story. I'm going to complete my presentation with this story. 1 minute, guys. Maybe I can share the slides. Okay. So, Anna Maria, the minute I share the slide, please let me know if my slide is visible.
Okay.
Okay, thank you. So now coming to the third part of the story, this is again a published work. If you ask me what it is, I hope you remember that the tannic acid and the gallic acid were very successful in functionalizing carbon nanotubes with them. But then there was a question from one of the editor asking us that what actually happened in, like, what can I say? How did this carbon nanotube and this tannic acid and gallic acid, how did they blend together? How did they come together? So this was one question where again, solving this took us again 6 months of time, and then we came up with a hypothesis. I hope all of you know what hypothesis is. It's something like a theory that this could be the happening. Okay, I'll tell you what actually happened. So here, now what I'm showing you here is the bundles of single-walled carbon nanotubes and multi-walled carbon nanotubes. Friend, I forgot to tell you one thing, that these carbon nanotubes, they exist as 2 different ones. One is a single-walled and the other one is multi-walled. Say for example, maybe I could show you with something. Maybe you take a paper, guys. I'm sorry, I do not find any paper with me. I'm sorry. Now, if you roll a paper, it is single-walled carbon nanotube. Just a minute. Maybe I can take a paper also. Okay, friends, listen. Say for example, if I roll this, Okay, if I roll this, this is a single-walled carbon nanotube. Whereas, if it is a multi-walled carbon nanotube, okay, guys, I hope you all can see. So there is one layer inside this. So this is how a multi-walled carbon nanotube will be. It will have layers and layers and layers and layers of tubes. Whereas if it is a single wall, it will be just a single wall. So these are two different carbon nanotubes that are actually in work. Okay. So we actually synthesized both single-walled carbon nanotube and multi-walled carbon nanotube, where you can see that all these are bundles of single-walled carbon nanotube. And here this is an individual network with traces of amorphous carbon. I told you when, what was his name? Saulo Santos. I'm not sure. He asked me a question. What was the material? So it is activated carbon. Here you could see some amorphous carbon impurities still attached. It is completely carbon and nothing more than carbon. So this was single walled, and here you could see some purified multi-walled carbon nanotubes where you could see 1, 2, 3, 4 layers here. But whereas here you could see all just single strand of hair. So this is one multiple stack layer where you could see 1, 2, 3, 4, 5, 6, and 7 layers of multi-walled carbon nanotube being produced. So this picture shows the kind of carbon nanotubes that we produced, both single walled and multi-walled. Now here you could see the FTIR spectra. Now what we did was we mixed this with tannic acid, okay, with tannic acid. And here you could see that these carbon nanotubes were highly carbon, and you could see nothing more than carbon. See, the peaks here could show you that all these are carbon. And here, when it is coated with the tannic acid and with the gallic acid, you could see the peaks of all these phenolic compounds being present. Now, this shows CH stretching, OH stretching, C double bond C stretching, and OH vibration of phenolic compounds. So, this FTIR clearly shows you that multi-walled carbon nanotubes existed with the tannic acid. Similarly, single-walled carbon nanotubes also existed with tannic acid, which means the functionalization, the mixing, the functionalization was completely positive. Okay, so if you could ask me what actually was the bonding mechanism, this is actually the bonding mechanism. So this is actually the schematic representation, which in short, I could tell you that this is the hypothesis that we gave out to the world. This is the interaction between CNTs and antioxidants, where here this is the structure of tannic acid and here this is the structure of gallic acid. Okay, this is the normal molecular structure of both these compounds. Now here you could see that this is a single wall carbon nanotube or multi-wall carbon nanotube, take anything for that matter. You could see anchoring of this tannic acid to the CNTs via pi-pi interaction. So this is where this pi-pi interaction exists between the hydroxyl group. So every tannic acid has got a hydroxyl group. Similarly, gallic acid also has a hydroxyl group. Therefore, there was an interaction between hydroxyl group of one gallic acid to hydroxyl group of other gallic acid. Similarly, interaction between hydroxyl group of one tannic acid to hydroxyl group of another tannic acid. So that is how there was a pi-pi interaction that existed between these compounds. And similarly here, gallic acid also, you could see pi-pi interaction. Therefore, it was like first layer of tannic acid followed by second layer of tannic acid, whereas gallic acid, it was only a mini monolayer with minimal hydroxyl group. When it was second layer, it did exist. Friends, I will tell you, there was a second layer, but the second layer was not stable. Only in case of tannic acid, the the second layer was stable. Whereas in case of gallic acid, the second layer was not stable. Therefore, with gallic acid, we found it to be a monolayer one, a single layer coating that was strong. Whereas with tannic acid, we found that 2 layers of tannic acid that was very strong. So this was actually the functionalization that we used with carbon nanotubes. So that's how this happened. That's all, friends. Thank you. And this is the end of the session.